Welcome to everybody. Probability and stochastic processes. In this session, we will study on operations on one random variable. That is, firstly, we will see expectation. I am Dr. V. Ayyambillai, Professor ECE GRIT Hyderabad, India. Expectation, introduction and modeling. In this, we are going to introduce what is expectation, and we are going to model an expression for expectation. Expectation on a random variable means the process of averaging on the random variable. The notation E of capital X has to be read as mathematical expected value of capital X, or expected value of capital X, or the mean value of capital X, or the statistical average of capital X. X bar is also used to mean what is meant by E of X. Next, let's see how we can model E of X for discrete and continuous random variables. Consider a collection of numbers A1, A2, and so on, AN. In this, please note that there can be repetition of numbers, though the names are different, but there can be repetition of values. We know the average of these numbers is sum of these numbers divided by the total number of numbers. There may be repetition of values of numbers. The average represents the whole collection of numbers. The average can be written as average is equal to A1 plus A2 plus and so on plus AN divided by small n. This expression may also be written as average is equal to A1 into 1 by n plus A2 into 1 by n plus and so on AN into 1 by n. We can recognize the above equation as sum of products of the numbers and their corresponding probabilities, where the probabilities are based on equal likelihood of numbers. For example, consider marks of 100 members in a class. For the mark of each member, we can assign a probability of 1 by 100, which is based on equal likelihood. Now, consider a discrete random variable, capital X, which can take up discrete values x1, x2, and so on, x capital N. Let the probability of different numbers be p of x1, p of x2, and so on, p of x capital N. Then we can write the average as average is equal to x1 p of x1 plus x2 p of x2 plus and so on x capital N p of xn. This we have written based on what we talked in the previous slide. On the previous slide, it was equal likelihood, but there need not be equal likelihood. If there is no equal likelihood, there may be different probabilities. So the expression becomes average is equal to x1 into p of x1 plus x2 into p of x2 plus and so on plus x capital N into p of x capital N. That is, E of x is equal to sigma small I is equal to 1 to capital N xi p of xi. For a continuous random variable, the expression is E of x is equal to integral of minus infinity to infinity x fx of x dx. Let's see an example for the concept of expectation. Let's consider fx of x is equal to 1 by b exponential of minus x minus a by b for x greater than small a, 0 for x less than small a. For calculating E of x, we have to write E of x is equal to integral of x into integral of small a to infinity x into 1 by b exponential of minus x minus a divided by b into dx, because for x smaller than a, the probability density function itself is equal to 0. That is why we are going for the limit of integration only from a to infinity. Now, for solving this, we can split the integral as follows. That is integral of a to infinity x into 1 by b e power minus 1 by b x e power a by b dx. Now we can take out e power a by b and carry out integration using the identity integral of x into e power ax dx is equal to e power ax into x by a minus 1 by a squared, where a may be real or complex. When we carry out our E of x based on this particular identity, we get E of x is equal to a plus b. Now let's see a function of a random variable and its expected value. Let capital Y be a function of capital X, where x and y both are different random variables. We will study the function, probability and mean. Let capital Y be equal to g of capital X. Then capital Y is equal to set g of small x, comma, where small x is an element of capital X. Now P of Y is equal to P of capital Y, that is P of small y is equal to P of capital Y being equal to small y, which can be written as P of capital Y is equal to g of small x, which can be written as summation of P of x, where the variation is in terms of x. Now when we talk P of y in terms of P of x, the summation comes in picture because one particular small y may correspond to more than one small x. An example is capital Y is equal to 2 into magnitude capital X. Now let's see the expected value of a function of a random variable. For discrete random variables, E of capital Y is equal to sigma small y into P of small y, where the variation is in terms of small y. This is equal to sigma G of x into P of x, where the variation is in terms of small x. Compare these two expressions. In one expression, we have the difference between these two expressions is in one expression we have P of y and variation is in y. In another expression we have P of x and variation is in terms of small x. For continuous random variables, E of capital Y is equal to E of g of x, which is equal to integral of minus infinity to infinity small y f capital Y of y dy. This is equal to integral of minus infinity to infinity g of small x integral of fx of x dx. Compare the two expressions. In one expression we have fy of y and variation in y. In another expression we have fx of x and variation in x. Let's see immediately an example. Let capital X be a continuous random variable with the probability density function fx of x is equal to x plus 1 by 2 for 0 less than or equal to small x less than or equal to 1 and 0 otherwise. Find E of capital X to the power n, where small n is an element of capital N, where capital N is natural numbers. So here we have y is equal to g of x is equal to capital Y is equal to g of capital X is equal to x to the power small n. Now E of capital X to the power n is equal to integral of minus infinity to infinity x to the power n fx of x dx. This is the fundamental expression. So that changes based on the given problem, that changes to integral 0 to 1 x to the power n into x plus 1 by 2 dx. Based on power formula, we get the answer to be 3n plus 4 divided by 2 into n plus 1 into n plus 2. Let's see an electrical engineering example. A particular voltage can be represented as a Rayleigh random variable V having the PDF as follows. Fx of x is equal to 2 by b x minus a exponential of minus x minus a squared divided by b, where small x is greater than or equal to a and 0 for x less than a. Let small a be equal to 0 and b be equal to 5. This voltage is applied to a device that generates a voltage y is equal to v squared, that is equal numerically to power in V for 1 ohm resistance. Find the average power in capital V. So we can call this V squared as signal power, that is power for 1 ohm resistance. So signal power in capital V is equal to expectation of G of V is equal to E of capital V squared. Now substitute small v is equal to v squared by small v squared by 5 and prove that signal power in capital V is equal to 5 watts.